In the last concept video, we discussed what is the shape of hybridization of BrF3. But some important points are there in BrF3 shape. When you say it is T-shaped, what kind of T-shape? So why it should have this kind of electronic arrangement? Why the lone pair of electrons cannot be arranged between the two fluorine atoms, and why the fluorine cannot push to left hand side and one of the lone pairs cannot be pushed in the right hand side? Which form is more stable? That is what we are going to discuss now. Now see, T-shaped molecule of BrF5. Okay, now supposing I am putting exactly T shape like this, and the electrons are arranged like this. So how do you account for trigonal bipyramidal? You'll see that. So this is your, the dotted line is trigonal and bipyramidal is two fluorine atoms. Okay. So now the dipoles will be oriented like this. This bond angle, what you are seeing, this is 120 degrees. This is a trigonal planar combination. So let me say this is figure A. Go to the, because this children, this concept will come as a competitive question for you. Which of the following is more stable? They'll ask you. Next, I can also make a trigonal bipyramidal molecule like this. So I can keep one fluorine here and the other fluorine here. So I'm sorry, BrF3, right? I'm sorry, bromine should come in the middle. So one fluorine is occupied in one vertex of a triangle, second vertices. So instead of one more fluorine here, I can put one lone pair here. And one of the fluorine can get occupied here. So this is this also trigonal bipyramidal. Other lone pair will occupy in the next apex of the pyramid. So this is figure B. Whether figure A is stable or figure B is stable, that's a discussion here. Okay, I can point out one more figure. Figure C. Figure C, what is going to happen? So same trigonal bipyramidal, I can put first. I'll put a triangle, right? So after I put a triangle, BrF3 once again, Br in the center. Okay, so in this place, all the three fluorine occupies three corners of triangle like this, single bond, single bond, single bond. Whereas in the axial positions, you will have two lone pairs. Now mind it, whenever I put a molecule like this, 1, 2, 3. See, this is y, x, y, like this. Now, these are all equatorial positions, and these are all axial positions. Say if you have, for example, if you take PCl5, lone pairs are not there. So, I can put y2 atoms here. In this case, this is axial, or you can have lone pairs over the axial, no problem. But I am indicating only the axial and equatorial positions. All of you understood which is axial, which is equatorial. In P block 15, 16 also we discussed. Okay, this axial, is equatorial. Now let me rub this. I have illustrated you what is axial, what is equatorial. Now coming to the stability. Arrange the following in the decreasing order of stability, whether figure A, figure B, figure C, which is more stable, which is less stable. See, please understand. In figure A, lone pairs are in the equatorial positions. equatorial, equatorial. So we can say that there is least lone pair repulsion. Therefore, this type of arrangement is highly stable. Coming to the figure 2, lone pair 1 is in the equatorial, the other is in the axial. Therefore, this is less stable compared to figure A, because in axial position means it is unstable position, understand that. Now the two lone pairs are in the axial position. My god, this is really unstable, highly unstable. 3 4 in the equatorial. So this is highly unstable. Why highly unstable? Maximum electron repulsion. This makes unstable. Therefore, I can say that figure A is more stable than figure B. Figure B is more stable than figure C. All are trigonal bipyramidal, but arrangement of lone pairs is very important. This kind of diagram can be asked, and they can ask you to arrange the increasing or decreasing order of arrangement of trigonal bipyramidal position. So this is a very important question. This is in accordance to VSEPR theory. Great.